Hey, this is Mr. Adomatis, and I am here in the classroom on a Saturday morning. It's almost Saturday noon. Oh my gosh. Recording a video because I want you to get the best score possible on your post-test. Because that would mean that you really know the science and engineering practices. Now, I'm going to go through the actual test, not the whole test, but just those parts of it that I think we need a little refreshing on. Those parts of the test that you have told me through formative assessment and self-assessment that we need a little more work on in order to do our best on this test. Okay? So, you're going to get the packet. Yeah, it's 60 questions, and you'll have a bubble sheet that goes along with this, and you'll be bubbling them in to your heart's content. The first thing that I want to touch on is the QFT protocol. That's the question formulation technique. And it's a productive way for you to start generating questions prior to a project or an experiment or something like that. Now, the important thing to remember about the QFT protocol is it's a brainstorming session. So this is not when you're not weeding out questions at this point. You might prioritize questions. That's one of the last things that we do. We prioritize questions, but we don't want to be judgmental about it when we're actually doing the process and telling people like, no, that's a stupid question, don't it? No, it might not be a stupid question. You might not understand what the other person is saying, so write it down anyway. And remember, then we talked about opened and closed questions and things like that. Now, I'm going to stop the video and give you a question just to make sure you're paying attention, and we'll do that as we go through sections of this document. Okay, let's move on. Most of this stuff in terms of, most of the stuff that we were doing about experiment design and hypothesis and that kind of thing, you guys did a great job on it, and I'm sure that you're going to be just flying through these questions, especially when we talk about a hypothesis and it's the way you format it is an if then because according to statement. You got this. You got it when we talk about independent variable and dependent variable and those kinds of things. One thing that we didn't talk a lot about, it was actually a sub-plan, and I never was out of work. I never took a vacation day or was sick to have a sub go over the how to use and refine models lesson. So let's touch on a little bit more now. Models are great, and maybe you've got some toy models around the house, and this is a physical model, right? And what it allows me to do is to see how the airplane looks from different views. Maybe I'm a sketch artist and I want to, sketch my airplane like climbing up into the sky or something like that. So this, just like if you were painting a picture of a person, actual model that you could sketch, like I could be using this airplane as a model that I could sketch too. Now, a model doesn't have to be physical. It can also be conceptual. Now, what do I mean by a conceptual model? Well, let me pull up a picture on my phone. And a conceptual model could be something like the food web. Maybe you've seen a picture like this before. So this is a concept, and you model it, and I say, well, let's see, the eagle is going to eat the snake, and then the snake is going to eat the mouse, and so you can kind of model in your own mind these concepts of how of the relationships between all the different critters and how they are related to each other in terms of the food chain or the food web. So that's a conceptual model. A model can also be mathematical, and we hit on this a lot in class. A model could be a graph. And this model, one of the cool things about a model is it allows us to predict. So based on the data that is represented in this graph, I can see that on any given Wednesday, I'm going to have about 100 deliveries. So that's a great way to use a model to be able to predict. Now, a model can also be an actual equation, like this equation of a line, y equals mx plus b, where x is representing our independent variable that's plotted on the horizontal axis, and y is the dependent variable, which is plotted on the vertical axis. For any value of the independent variable, I could go up here and where that hits that line, then I could come over here and predict what might be measured for any given thing I manipulate. So, graphs and equations kind of work hand in hand, right? So they can both be models. Now, there are limitations to the models. Of course, this is not exactly an airplane that I can climb in and fly. I mean, it's a reduced version of it, and it has limited capabilities. A model is only as good as our current knowledge. So, say if we were modeling the atom and we found something out new about the atom, then all of our current models would change. And so, just because a model was developed by a scientist at Clemson, would that make it a better model or less of a model than a model that was developed by a scientist at the University of South Carolina? I'm going to let you answer a similar question like that. So one more thing about scientific models that you should know, it's kind of like the engineering design process. Oh, now I've lost my collections here. Oh gosh, well, I guess I won't be going back to that. Remember that scientific inquiry and engineering design and model development are cyclical processes where we have an initial design or prototype or hypothesis, and then we build it, we test it, we analyze the results, and we see, based on those results, we make improvements to the model, we refine it, we test it again, we analyze it. Same thing with a model. If the model suits our purpose, great. If it doesn't suit our purpose anymore, then we may need to refine the model. Same thing with scientific inquiry. If our hypothesis isn't supported, then maybe we need to revise our hypothesis, do another experiment, and look at the results again. So remember these cyclical processes. And we'll do that again and again and again until either the boss tells us, hey, we ran out of money in your budget, stop doing it, or we get to an answer that we're satisfied with, at least for that period of time. Okay? I'm sure you guys know how to plot scientific data and graph it, so we're going to skip over this section too. But when we get into data analysis, that's where you guys told me that we really need to, have some reinforcement. And this whole idea of the correlation coefficient, I know you guys don't take statistics in high school until you're, I don't know, a junior or senior, or at least a sophomore, right? But I do want to spend a little bit of time on the correlation coefficient. Its mathematical symbol is R. Those two things are R. That is your correlation coefficient. Important to remember that. And it's a measure of how well the variables are related. For example, let's see. This obviously all these points would fall on a nice straight line of best fit. That looks like a really good correlation. We call this positive because it has a positive slope. But it doesn't. Correlation lines of best fit doesn't have to actually be a line. It could be a curvy line, right? And so we could have a curved line of best fit that would have good correlation. Okay. Now the strength of the relationship, the strength of the correlation, it could be strong, like we see. Obviously, these are all falling on a line. It could be a little bit weaker. We see a trend in the relationship between these two variables, the independent variable and dependent variable, but it's a little weaker. And then it may just be a total and complete scatter of data, which we say, well, that's not really correlated. And the way we express that numerically with an R value is a value that is between a negative 1 and 1. All right? So between negative 1 and 1, we have a 0, right? 0 is equal to totally uncorrelated. That would be this scattering of data would have a correlation coefficient of 0. Now, 1 just means that it has a negative trend, and a positive 1 means it would have a positive trend. Don't let that worry you. Sometimes we square the R-valued component, so it would never be negative. And we do that just to, I don't know, kind of simplify things so we don't have to think about negative numbers, I guess. So keep that in mind when you have this question on the range of possible values. Now, another thing, when we do experimental analysis, we look at the percent error. We just want to know, how good is the value that we got compared to what is the acceptable value. And you're given a little equation for that. These two vertical lines, I don't know if you've gotten that far in math, but that just means that we're taking the absolute value of the quotient here that's inside. That means we're never going to have a negative value for percent error. That just wouldn't make any sense. It's important that you get the order of things right. Theoretical value in the numerator, theoretical value minus experimental value. All of that divided by the denominator. People get into trouble where they don't do the order of operations right. So keep that in mind when I'm asking you to hand calculate a value there. Okay. The way I remember this, if I wasn't given the formula, is that theoretical is the most important value, or the most accepted value, and it's mentioned twice. So theoretical minus experimental over theoretical. Okay, let's look a little more closely at these correlation coefficients and what they might look on graphs as we compare them. Now, take some time during the test and look at these 4 graphs, and I think that you'll agree that graph A looks like the best possible result that you could get, because it's a tight scattering of data that's falling on where the data points are falling on either side of this line of best fit, or this theoretical value. Graph B, it looks like we have good correlation, but they're falling away from this theoretical value, and that's the difference between the line of best fit that we would draw here and this line of theoretical. That's actually our experimental error. So this would be good correlation, but we have some experimental error. Recognize that in graph D we have a large scattering of data, so there would be low correlation. Now C is an interesting one because, well, it looks like we have low correlation, but if you actually calculated the experimental error, because these points are looking like they're equidistant from the theoretical values, if you averaged them, they would actually fall on that value. So that's a little tricky one, right? Okay, but just a lot of these questions, it just takes you some time to think about. So I'm going to move on. I think you guys know the difference between linear and nonlinear. Some of these shapes might look a little bit weird. This again comes into vocabulary, knowing what an inverse line looks like. So please do review your vocabulary. I'm going to come back to this graph here in just a little bit. As a scientist, I want you to be able to construct explanations of phenomena. So as we get further along in this test, now we're into question numbers 40s, 50s, and it goes up to 60s. This is the stuff that we haven't covered a lot. So I want to provide you with some help on that. And a lot of this stuff is, it's like English or literature. If you're a good analysis of someone, if you could analyze someone's story, you're looking for the same kinds of things. So there's a lot of writing here, which means you're actually going to have to read. But we're all talking about, we're making claims over here. Like, for example, tooth decay is caused by by candy. That is a claim, and we're trying to determine whether that's supported or unsupported. And the key to answering these questions correctly is to realize that support for a claim has to come through a good explanation and evidence for that explanation. So when we explain things, we say because, right? And so, remember that in a hypothesis, we have a because that's a statement in our own words of some sort of theoretical thing that we've looked up from a credible source, right? So explanations usually have the word because in it, and evidence, you're looking for, according to the data, or we did an experiment, and those are the kinds of things. Now, just because someone say there's facts involved doesn't mean that there's data, right? Because you might present, well, let's not get too lost in that. Look for experimental data as evidence when we're talking about scientific claims, okay? All right. Now, when we get into this whole thing about argument, remember that when you write a hypothesis, your argument, your claim is that because part, that explanation that you have in your own words. Your if and your then have to do more with the variables that you've identified and the how and the whys of the relationship, the how those variables are related. Why those variables related is your claim or your argument. And then the according to part of it is really you pointing to the credible source of information which supports your rationale and your reasoning of what you've said in your hypothesis. Remember, validity is a valid, credible, reliable. Those are all important vocabulary terms. Please again review your vocabulary. Question number 53. I don't know if interpolation and extrapolation are in your vocabulary list, so let's go back to that graph 42 and 44. Questions for 42 and 44. What I've asked you to do when you graph, if you plot values and you have a lower end of the range of values and an upper end of your range of values, I say that's where you want to draw your line of best fit. Now, if you want to extend that, please use dashed lines because you really don't have data beyond that upper limit, right? So it might, this looks like a straight line, it might be safe to say within reasonable limits that it might continue to be a straight line, but however, you don't know. It might continue to go up, or it might be a balloon that goes pop and comes right straight down. You don't really know that, right? So extrapolation is beyond your range of data, and interpolation is within your range of data. And it's a safer bet that if you pick a value right here, then you're going to be able to make a better prediction about the results that you would get. And I would hazard to guess that you would also have less error in your prediction. You would have less experimental error when you're interpolating rather than when you're extrapolating. Okay. Question 54. There's a lot of writing here, but save yourself some time and look for these words that Mr. Adomatis does not like to hear. I don't like to hear that we've proved anything in science because basically we just support our hypotheses and theories can change and we revise what we know. Whoa, the light's turned off in here. Turn back on. I'm here. Really, I'm here. Okay, well I guess we don't need them. Oh, there we go. And also, anytime I hear words like believe or I think, those aren't words that lend themselves to be very convincing, all right? We want to say things like according to the data and just to be really strong and supportive. Okay, coming up on 20 minutes here. Mr. A, are you ever going to finish this stuff? All right, so let's look at the last part of this, evaluating scientific information. On question 57, look for bias. Look for non-bias. If something is being sensationalized by some guy that in the mall that is, trying to sell you something, he's going to use a lot of convincing language and because he's trying to get your money, right? And so you want to look for non-biased sources of information that, you know, come from educational institutions or government agencies or things like that, not commercial enterprises, right? Number 58, if you know the definition of bias, then you're going to get that answer correct. As we get a little further down here, I don't know that we ever really talked about peer-reviewed, but if, let's say, I wrote a paper about good teaching practices, it wouldn't be good to have one of my students review that paper because, you know, I might have been giving that student candy just to give me a good review or something like that, right? A peer review, my peer would be another teacher who might have some comment as to, you know, how good my teaching is, okay? So listen, that was really hitting on some of the more difficult questions in the science and engineering practices. If you review your vocabulary, I think having had watched this video, I think you're going to do well, and I can't wait to see what you do.